This talk is called The Big Lie of Big O. So does everyone know what Big O notation is?
I've heard of it. I don't know what it is. I still don't know.
Right, because it's all academic.
Yeah.
For those that do know, how many of you have used it or thought about it outside of an academic setting or job interview? Okay, good. Can we prove it? We can all go home. No. Yeah, it doesn't. Well, I do want to talk about it because there are some interesting things that come up from it, and it helps you think about efficiency, performance, but not the way that Big O was originally intended to think about. So the inspiration for this talk came up from a YouTube video I watched by the channel Computer File, which is put out by the British. Yep, if you're familiar with it. They put out a video, I think it was like 6 or 7 years ago, about arrays versus linked lists, which is faster. And I have the QR code right here, so let me just hold on. We'll get that. And you know what? That's going to take too long. I got it right here. If you want to see it, you come up and scan it, and then you get to the video. You thought I was going to see here. If I drew it out right?
I just saw the Veritasium video.
Yeah, we made it with the Go. Yeah. Oof. Nah, it's kind of crazy. So in this video, what they did is created a very simple program that went through, built out, I think it was like 1,000 or something numbers in an array or a linked list, went through them all, summed them up, and then put out the output and saw how long it took on different systems right there. And that's what Big O is doing. When you look at those different versions, it's all the same Big O. So the way Big O works, because some of you don't remember right here, but it's basically you're looking at your code and you're seeing all the paths that you take, and based on the paths that it's taking, you're adding or subtracting or doing something to a number of n. So Big O is normally written O of n, meaning that for every item or every parameter in the function, you have to go through it once, right? There's also O of 1, meaning no matter what you put in there, it's always going to be constant, right? You have some other examples. You'll have O(n) squared, meaning you have to do things exponentially for everything. So this would be like a for loop and a for loop kind of thing, or a recursive function calling itself over and over again. And then you can, well, actually, this is not a recursive function. This is a recursive function, which is O log n. And every time this number gets bigger, the theory is your program is less efficient and not going to work as well. But let's think about that for a second. So I'm going to give an example right here, because I put this out on Twitter back when I had a Twitter right there. So I have a function that takes an A and B, and it returns A plus B. Now, based on what I just said, what would the Big O for this be? Any ideas? O of 1. Why is it O of 1? So it takes the same amount of computational power no matter what I put in for A and B.
You put the same things in for A and B. If you put A is equal to 3, B is equal to 3, it'll take the same amount of time.
Now let's think about computational power of processing outside of a computer for a second. So let's put this to the test. 9 plus 5.
14.
27 plus 38. Okay, it's not 1. Already it's taking me longer to do that. 893 plus 437. Every time, right? So we think, yeah, exactly. So to start, we thought this was O of 1 because it's always constant right there. But as we saw, every ordinal that we've increased, every digit that we added to that number, we've increased the amount of time it took us to process that. Now, you may say, well, computers can do this really fast because it's all in hardware, right? So it doesn't really matter at that point. Well, let me ask this question. What happened? Does anyone here know how a CPU actually works at the end of the day with bits and binary addition and all of that stuff? All right. So basically, you're filled in a specific set of digits that you can use, places that you can use for numbers. So we're all familiar with 8-bit, 32-bit, 16-bit, all of that right there. So let's imagine we had a 4-bit processor, and this is not so far outside the realm of possibility because it was one of the first microprocessors invented, was a 4-bit microchip, and it was used for calculators. I have here a picture of the very first calculator that used it. This is called the Busicom 141PF. This is way before TI-83s. It's right here. It's not a room. It was considered portable, right? This used the Intel 4004, excuse me, the very first of its kind. 4,000. Yeah, exactly. It was able to do 15 digits, but with 4 bits, there's not enough space in there. So how did it do it? Well, it did stuff using a lot of shift registers, which means it would move the bits along as it was adding and throw stuff into memory, right? But that's the first point I want to bring up. Hardware is your first step when it's coming to performance. When you're thinking about stuff, you can't just look at your code and be like, oh, it's going to perform well. You actually don't know what the compiler is going to do, you don't know what the operating system is going to do, and you don't know what the hardware is going to do. In that video, what they did is they ran it, and I'm going to pull it up right here. They ran it on 3 different systems. They ran it on an old Atari computer from the 80s. I forget which model it was. They ran it on a current iMac, and they ran it on a Raspberry Pi. And the way they compared everything was clock ticks, which is computational complexity and processing, which is what big O is supposed to represent. So I'm going to write them down here. The Atari, when it was doing a linked list, and again, you don't need to know about linked lists and arrays, just know that each one was still O of n in terms of the code. It took 166 clock ticks to do linked lists, 178 to do the array, and it also did array reverse, where it started from the back and did the beginning, and it did 114 clock ticks. On the Mac, for linked lists, this was interesting, 209, 43 for the array, and 47 for the array in reverse, which is interesting. Yes? I'm going to get to that in a minute. And then for the Raspberry Pi, for linked list, it took 1858, 965, and 1019. So what the hell is going on here? Why are all these things very different? Does anyone want to take a guess before we go into it? Hardware. What about the hardware, though? What's happening?
Hold on a second. You asked the one question.
What do you think about the hardware, though?
I'm assuming there's not a lot of memory in there.
Well, again, this is normalized out for that because this is clock ticks. No. The number of clock ticks. So every time a processor does something, it does it on a tick. So it does things one at a time in each clock tick. So even if this is 800 megahertz, this was gigahertz and everything right there, we're talking about the clock ticks itself. So you can't look at it that way. It is the architecture, yeah. So basically what's happening is this. In the Atari, it doesn't have any caching at all. So every time it needs to look at something, it has to go out to the hard drive or RAM or whatever address space, get that information, and then act upon it. The iMac, nowadays, has different layers of caching inside of it. It's normally called L1, L2, L3. If you're into like gaming and performance, you'll know what those mean and everything like that. But basically, all the data is loaded inside the CPU into very fast memory that it can access very quickly and get things done. And the Raspberry Pi, it's got some caching, but it's a different processor architecture. The Atari was a 6502, which is a very famous processor, still in use today. The iMac, this was before M1, so this was the power. This was still an Intel Mac, so it was an 8088, 86, excuse me. And the Raspberry Pi was using ARM, which is mostly in your phones and all that. Now, what's interesting, there's other layers to this. So I mentioned the hardware part, but then we had the compiler in between. And the compiler is optimizing the memory space very differently for these things. So in the iMac, the reason why linked lists was way slower than the array was because what's happening is the compiler is looking at it and thinking, oh, I have all this stuff that I have to do inside of this loop, So I'm going to put it into one continuous block of memory that will fit inside of that cache, and I'll have direct access to it right there. Also, it also has what's known as pipelining, where it can look ahead to see what the instructions are that it has to do, plan ahead of time, and sort of make everything available so that when it actually gets to the point of execution, it's right there and ready to go. And that's when you're like mixing in these different parts. You're interleaving the loading in the code, decoding what you have to do, getting the memory, doing the actual code, storing the result. All of that can be done synchronously at the same time, which is very interesting. The Raspberry Pi on the ARM is optimized for low power, low voltage, because again, ARM processors are mainly used on phones. Another interesting thing that comes into play is what the compiler is actually doing when you give it instructions. So for instance, let's say you want to divide two numbers together. Now, without going into the weeds, there's a couple of ways that you can do that on processors. Modern day processors actually have an instruction where you can say, divide this number by that number. Before that, because the Atari and, believe it or not, the Raspberry Pi and a lot of phones can't do division natively in a CPU. They have to do some crazy binary math of shifting bits around and everything like that. It was actually found that in some cases, it's more performant not to use the native instruction on the hardware, but to actually do the bit shifting because it's very quick and very efficient processor to do that right there. Whereas all these extra circuits and logic and code that have to go into the CPU to actually do division slow it down directly. So the point I'm trying to bring up here is that when you're looking at your code and you're trying to optimize it, there are so many factors that come into play that you don't know what is going on under the hood. When you're requesting memory in your program, the operating system is going to segment this out and keep you isolated from other stuff for security reasons. So there's all that logic that comes into play. Then when the operating system's asking the CPU to do it, the CPU is going to be like, oh, well, I'm doing something else right now. You got to give me a second and let me finish that up here. And let's get into GPUs for a second. CPUs do things sequentially. They do things in order, and they're very good at that. Believe it or not, this is the way it was for a long time, and it blows people's mind when it's like, nope, the CPU is only doing one thing. When you're having multiple programs run at the same time, this actually was a problem back in the early computing days where you would have program A interfering with program B. Nowadays, that's not a problem because of the way the CPU, or excuse me, the operating system is controlling access to the CPU. GPUs, on the other hand, do things in parallel. So there are some cases, for instance, this code where it was going through all the linked lists and doing everything could be done at the same clock cycle on a GPU because what you're doing is just saying, here's my data. For each item in here, just add these two numbers together. And it will do it at the same time, whereas the CPU has to walk through it right there. When you're optimizing your code, you have to think about all of these different cases that come into play. And a lot of times, you don't even have control over it. So if you're in a higher level language, for instance, I work at JavaScript, I don't have access to the CPU. I can't say, do this code on a GPU. Python lets you do it, but you can't do that in a browser. You can't do that on a web page. So you have to be careful on what you're doing there. When you're building out and designing your systems, you need to take a look at what you need it to do, get it performant as possible for the hardware that you're using. If you're not sure what that is, define what your hardware is, because otherwise it's going to slow things down. Another interesting thing about this, because we were talking about the speed. So you brought up the speed. Now let's bring up the speed. This right here for the Atari took about an hour to run. Because again, it was like a megahertz processor, old, took a while to do. The iMac completed it like that. Like you barely saw it. Barely did a ding on there. The Raspberry Pi took about 2 to 3 minutes in the video. Because again, all the different stuff's going on. How many people are going to wait an hour for a web page to load? How many people are going to wait for 2 minutes for a web page to load? Right? What's that? I know. I remember it took. Exactly. Mm-hmm. Hey man, I was on the BBSs as well too back then, so that's. But the point I'm trying to make is that even if we look at something that was O of 1, which is the most optimized, performant, big O out there, if O of 1 actually equals 10 minutes, where O of n equals 300 milliseconds, do the O of n, even though it's more computationally complex. The point is that you're delivering your product faster to your users. So we talked about the hardware, that the compiler is going to optimize things, the operating system is going to optimize things. At the end of the day, your customer does not care what you're doing on the background. You could have wrote the most amazing, beautiful code that you've ever seen. You can win a Nobel Prize for the code that you wrote, right? But Johnny in the coffee shop who's browsing your website doesn't give a shit if it takes 10 minutes for it to load. Look at your code from that point of view, and then you'll start writing more performant code.
So this came to your mind because we get a lot of CS students here, a lot of master's degree CS students. We talk a lot about code and theory,
Right.
But that doesn't necessarily map to what's happening in the real world. So
No.
so give a little context for non-technical folks, lots of students out here that are running through this, like what we're learning in the classroom and how it applies to real life is a wrinkle.
Yeah. So I was. So I do a lot of DevOps as well too, in terms of developer advocate as well. And one of the jobs I had when I first came on, I was talking about building out this entire system where pretty much like what you had. You had CloudFront with S3 buckets and caching and Redis and all this stuff going on right there. The guy I was mentoring for it, he goes, "What's the big O of all this thing?" And I'm like, "What's the big O of all this? It's insane, actually." It's going to be O of like 10,000 and 10 to the power of 10,000 because you have all these different complex layers coming into it. So one of the things, well, let me do a little brief history here for a second on why this was so prevalent in academia and still kind of is today. And I just got to look back at my notes because I don't have slides because I have a whiteboard up here. All right, so
Seems like a jab.
what's that?
That seems like a jab.
I'm just saying. It's fine. I'm adapting, right?
There you go.
Okay, so here's the timeline. Here in 1894, this was when Big O first came into the mathematical space. It was used in applied number theory. Again, it was basically to say which equation was best to figure out prime numbers, because we're doing stuff by hand at this point, right? Then it stuck around for a while. 1904, it started getting adopted into formal number theory sets. Here in 1950, we start having these things called computers come along. And they're all built on different systems, different hardware, different code bases, different instruction sets, and they're all optimized to do very different things. During this period, computer science and mathematics were very intertwined together. So whenever you talked about something in computer science, you talked about it in a mathematical sense in the formula. And Big O sort of got adopted here because you had all these different hardwares that were doing things very differently, but complexity in terms of how efficient an algorithm was very difficult to quantize and standardize across every different board right here. So for instance, the ENIAC was very good at doing missile projections, whereas you had the PDP at the time was very good at matrix calculations. Good for math, good for businesses and all that. I could be wrong on that, or switch them around, but you have the good idea. So then the 1970s come along right here. And this guy, Donald Knuth, is working on computers. And that's when he tied it into the instruction sets and the code bases. So now we get these higher level languages coming to play. COBOL, Fortran, C is invented around this time. You had Lisp, all these different languages coming in. And we didn't know how well these things were going to work together. So that's when Donald Knuth came up and said, well, we had this thing from number science that's been around for 60 years now. Why don't we use that to determine how efficient a language is and how well it's working? And that's sort of how it got into our vernacular. But keep in mind, during the 70s, you had these high-level languages that would today be considered low-level languages. So for instance, C is a low-level language in terms of what we're doing, how close you have access to the hardware. All C is really doing is taking your code and translating it into instruction sets for the processor. It's doing a little bit more than that, but I'm trying to keep things simple here at the moment. And especially in the 70s, that's what most languages were doing. Nowadays, we have scripting languages, and a lot of these are actually built on top of C. Python's built on C, Node's built on top of C. Some stuff, Go is its own thing that wasn't built on top of C, but now kind of is built on top of C. It's a whole thing. Objective-C, all of this. So you have these higher level languages, which are relying on the lower level languages, which are, again, relying on these other things coming into play. But we still talk about it in academia because it's easy to take the abstract concept of a function and then work out how performance is going to be without getting into the weeds of all this other stuff that I've been talking about, which is why it's still around. Now, the problem I have is when you take it out of the academia setting and you try to cram it into the real world, it doesn't work. It breaks down. And we just proved that based on this video right here. So hopefully that kind of answers your question right there. This is when your mom was born. Right? So most of the time, when we're asked the question what the big O is, in an academic setting, it's a teacher trying to see if you're grasping what is being taught. In an interviewing setting, I'm not really sure because of the fact that in an interview, you're trying to gauge someone's strengths and weaknesses based on what they're building, and I have a whole other talk about the tech interview and the problems there. But you don't have enough time in an interview to go into those weeds and talk about it. And I give a famous example. Back a while ago, I'm not going to say when, I was interviewing for a company. And it was funny because this company, when it was pitched to me, was, oh, you'll be working with this guy, Steve or whatever the hell his name is. He's a genius. He's the best guy ever. He's the smartest guy in the world. You're going to love working with him. And I asked him what the tech stack was before going into the interview. And he had 5 different CMSs on top of each other. And this was back in PHP, so there was CodeIgniter, CakePHP, there was Drupal, WordPress, and like another CakePHP all on top of it. What the hell is up with this? I don't know why you need 5 content systems on CMSs on top of each other. So I go into the interview, and again, it's a PHP job, and it's important, I'll get into it. The guy has me write a function to do Fibonacci on the whiteboard. Straightforward, I do it using a loop. There's like 7 different ways to write Fibonacci, and each one of them have different levels of complexity in terms of big O. Like some of them can get to like really crazy levels right there where you're doing crazy stuff. But I went through and I did it in a while loop. And then he asks me, is there another way to do it? And I go, I could do it in a recursive function, but I wouldn't. And he goes, what do you mean? I go, well, this was PHP. PHP 4 world was still big right there. And for those of you who don't know, PHP was a memory hog when it came to functions because nothing was passed by reference. Every time you called a function, it would take in all those parameters and copy it into another space inside of memory and keep doing that and doing that and doing that. So when you're doing a recursive function, you're going to exponentially grow out your memory. So not only was this function that he had me write, O log n, it was actually O log n squared because of all the memory space that had to be done, and then all the garbage collection after it. I actually told the guy, I'm like, I would never put that into production, explained it for that reason, and then he actually said I wasn't technical enough to be there. So kind of interesting editor right there. But I was able to articulate why I chose the code the way I chose because of those different reasons. Because I knew if I did this as a recursive function, it will be terrible. All the user has to do on the website is pass this thing max int. It's going to crash the service, and we're not going to know why, because the logs would have been destroyed in heat. The logs would have been destroyed. So, but yeah. So that's why I'm an advocate for let's stop promoting this stuff outside of academia. I get why we do it. I get why it's there. I think we spend a little too much time on it because we're talking about it in the wrong way. As I just explained, we're talking about it from a theory aspect and just statically analyzing our code. But when it gets down to it, you're going to have your instructions. You got to make sure that it's performant. You got to make sure it works. Right.
I felt like I was watching a computer farm video right now. It could have been brown paper right there. And
I've
the
been
same
saying
shit.
libels and everything.
Yeah, it would have been great. And then, you know what, the thing that was interesting too that you reminded me of is Matt Parker's video on Wordle.
Yes.
And the follow-up video, which was all about like, you know, optimizing the code, because his initial code was an entire month.
Yeah.
And then like literally he posts it and it was like, oh, I can fucking do better than that.
Yeah.
And now it's down to like milliseconds running that thing, which the really interesting part about that too is he identified, or I guess that group identified that all of the time that it was spent was actually reading the goddamn file.
Right.
Not the compute that was happening afterwards. It was trying to figure out, all right, how do I read this as fast as possible, such that I think toward the end he was saying it would run the words through the program before even finishing reading the file.
Exactly.
And that would even speed it even faster.
Mm-hmm.
Yeah, so really interesting to see the different ways of doing it and how that affects the compute time, and then of course what you're talking about in terms of like how those things, I'm sure they were optimizing the O and all of that.
So when I worked with the company that did the Elf Yourself thing, we had to come up with a way of efficiently storing all of these images on a file on the server so that it can be served up by the server that's processing it, and then at the end of the day to the end user right there. If we just kept everything in one big directory, it would take forever to seek through. The operating system just bogged down. This wasn't that long ago. It was about 15 years ago. So, you know, stuff was performant then. But we were using 32-bit servers at the time because 64-bit was still coming out at that point, and they were still very expensive to use. We then found if we were to, so what we did is every file that got uploaded, we basically just hashed it, and it would just give us a string, letters, and numbers right there, and it would be like, you know, ABF32ZGX.jpg or whatever right there. We actually found that if we took the first the first 4 letters, and then chopped them into 2 bytes, so if it was ABCD, you would have AB and CD, that would be your directory. So your directory would be AB and then CD, and then the file would be inside of there. By breaking it up that way, we actually reduced loading time on the operating system, the I/O on the operating system, by a factor of like 500. I think we worked it out right there. Because now what's happening is the operating system is optimizing where all the files are being stored in different sectors. It's optimizing its database of where all the files are, so it can serve them up faster in the end. So again, that's another thing that like wasn't considered when we were first building out this project. Mm-hmm.
I'm going to ask, based on the shirt, does the master not approve of the notification?
The master does approve. You know, it's funny. I just had a kid. It's going to be 10 months next week. And I started my Turkey Day marathon on Thanksgiving. I'm only on season 9 right now because I just can't find time to watch it.
What do you think of the new stuff? I think it's okay.
Yeah, I think it's fun.
Sorry. Diversion about
Mystery
Science.
Yeah, Misty's.
Now it's your time, so you guys can continue that conversation if you want. Chuck, thanks so much, man. Does anybody have any other questions for Chuck?
Does anyone want the QR code for that video?
Yeah. Team, we have like maybe 30 minutes left before I got to start tidying this place up. So the rest of the time is yours. Feel free to introduce each other and see how you guys can collaborate. You two should connect on your viral video marketing. Let's capture that. But thank you all. We're going to do another one of these probably in about 45 days. We're looking like the second week of March or something like that. And yeah, if I haven't met you, please come introduce yourself. I'd love to meet you. Cool. Thanks, guys.